Now we come to another outer bound from Körner and Marton. So this outer bound was the best one known to 2006. In 2006, we will come to it later, there a new outer bound, a better one was found. So the outer bound is in principle very similar to the Gelfand-Pinsker converse. So we can use the methods we use there, and we will also not do the original proof, but we will use again this idea of Gerd Kramer by using this telescope sum. For R1 and R2, the proof is exactly the same like in the Gelfand-Pinsker case. Therefore, we do the more general case when we look at R1 plus R2, n times R1 plus R2. Then, using Farnow's inequality, we get in the same way as for Gelfand-Pinsker, we get the mutual information between W1 and W1 hat plus the mutual information between W2 and W2 hat. You just can look at the proof. I wrote it down for Gelfand-Pinsker exactly how to use the Farnow inequality. And if you now insert instead R1 plus R2, you get exactly this result here. This we can estimate by the mutual information of W1 and Y1 to the n and W2 plus W2 and Y2 to the n. So you see this is a function of this, so we can insert this here, and here this is a function to this, and we add here this W2 here. When we add this, we use this idea of a telescope sum again. So we can write this mutual information as this sum plus this sum here. And if you just look at this, and sorry, here's a misprint, it's also in the script, it must be Y2 to the 0. I think it's also misprint for Gelfand-Pinsker. The 0 must be here upwards, not downwards, because this here is 0 if it's 0. So if you put just all sums here in, all sums here in, and write them down, you will see that this one only remains. And why is this trick good? Because now we can extend, like we did for Gelfand-Pinsker. We just leave this, and now we extend the sum just by adding here this mutual information and subtract this mutual information again. So it's really the same. We just add this term here and subtract this term here. And then we can write the same sum in this way. Why we do this? Because now this here is equal to this mutual information, and this part here is equal to this mutual information. That means we can simplify this. Now we set u to I equal W2 times y to the n 1 of I plus times I plus 1. It's y1 from I plus 1 to the n and y2 I minus 1. So this means here it's from the I plus first position to the nth position. It's the same notation we already used in Gelfand-Pinsker. That was already on the previous page here. We use this notation. This means y2 is the random variable, and here y1 is a random variable, and here we look here at the position from I plus 1 to the n. That is this notation. If we just write here I minus 1, then it's just y2 of length, the first I minus 1 values here. So now let's continue. If we insert there u, I, then we can write this as entropies, then we get this equation here. This we can estimate by leaving out this condition. Then this only can get bigger. So all the others you see, we just take the same values, and here it's minus, we make it bigger just by adding a condition. And if we write this like this, then we have the mutual information of ui and y2i and of xi and y1i under the condition ui. Yes? And again, we sum from I equal 1 to the n. And now we use the same idea as for Gelfand-Pinska. We maximize this here over I and take this value here. And if we take this value n times, then this is bigger than this, and we have n times the maximum over all I, and then the mutual information here, and here we have n times R1 plus R2, then this n cancelled out, and we can estimate it by the mutual information of u and y2 plus the mutual information of x, y1 under the condition u. That you can see here on the next slide, then we can estimate it like this. It's the same stack like Gelfand-Pinska. Also, these two estimations are done in the same way like we did for Gelfand-Pinska. And if we now set R0 equals 0, then the capacity region is for all non-negative R1 and R2 satisfying this inequality. So this is a converse for this part. So now in the next step, I will present you the whole bound, also if R0 is positive of Marton and Körner, and then also the improvement of the bound.